Welcome back. Let's look at 3.5, where we introduce a new idea. It'll be related to boundedness before we're done with this section, but the new idea is the idea of a closed linear operator. So we'll give another property of linear operators, and we'll see that this property implies boundedness under appropriate hypotheses, and boundedness implies continuity, as you know by Theorem 2.6. So we're going to define the graph of a transformation in a very general setting. We're going to use it in a more specific setting, but in general, for T, a mapping from set X to set Y, we're defining the graph of T, denoted by G sub T, as a set of ordered pairs XY, such that X, of course, is from the first set, Y is from the second set, and the transformation, the function in general, plays the role that y equals t of x. So these are the ordered pairs we get out. This is a subset of the Cartesian product of x and y, and something awfully familiar to all of us, because this is just the idea of a graph in the sense of high school algebra, y equals f of x type graph. It's the collection of all ordered points on the graph. So this is defined in the setting of, if you like, we could treat x and y as sets. Of course, we need more structure than that to do what we're going to do. In this section, we'll take x and y to be normed linear spaces. We might even take them to be Banach spaces before we're done, but certainly normed linear spaces. So we can view x times y as having the sup norm on it. So that would be for the pairs x, y, we define the norm of that pair to be the maximum of the norm of x and the norm of y, given that sets, well, spaces, linear spaces x and y are normed. So we've actually got three norms here. We've got the norm on set x, the norm on set y, and the sup norm that's being defined on the Cartesian product, x times y. So anyhow, if we've got a norm on the Cartesian product, then we've got a metric on the Cartesian product, and that allows us to define open sets and closed sets in terms of the Cartesian product. That allows us to put a topology on the Cartesian product. The norm induces a metric, the metric induces a topology. But ultimately, the punchline there is we can talk about open and closed sets. And it's the closedness that we're interested in this section. So a linear operator, T, is defined to be closed if its graph, G of T, is closed in the Cartesian product, x, y, where we take the sup norm ideas just introduced. So closed linear operator means topologically closed graph, topologically closed in this Cartesian product. We'll have three results. The first says if T is a linear transformation from x to y, it's injective, it's 1-to-1, and it's closed, then T inverse is also closed. Of course, we need the 1-to-1ness to even discuss T inverse as a linear transformation. But the claim is, under appropriate hypotheses, the existence of T inverse. If T is closed, then T inverse is closed. Let's look at a proof of that. All right, hypothesis of T, a linear transformation from x to y, which is injective, 1-to-1, and closed. All right, we're going to approach this by showing something is closed. Ultimately, we want to show T inverse is closed. By definition, that means the graph of T inverse is closed. So that's what we need to show. So we're going to consider a point in the closure of the graph of T inverse. And we're ultimately going to show that the graph of T inverse itself is closed, thus giving the conclusion. So I'll take a point related to the graph of T inverse would be of the form y comma x, or lowercase x and y are from the obvious places. But take a point in the closure of the graph of T inverse. We know, we're applying Theorem 2.2 point A, part 3, again, actually a couple of times in this argument, which says the closure of a set includes all points for which there's a sequence of elements of the points in that set that converges to. Let me try that again. If I take a sequence of points in the set and that sequence converges, the limit point will be in that set. And conversely, if I have any point in the set, there is a sequence, of points in the set that converges to that point. So we'll take yx to be in the closure of the graph of T inverse. We know there's a sequence of elements of the graph of T inverse that converges to that point. Okay, we got to deal with ordered pairs because of the setting here of a graph of a transformation. But since this is in the closure of that set, then there's a sequence of elements of that set that converges to the point. That's what Theorem 2.2.a part 3 says. It's all about, we've used it several times, it's all about classifications of the closure of a set. So oftentimes we dealt with sequences. Yeah, oftentimes we dealt with Banach spaces too. Not here, not yet at least, with the Banach space stuff. So we're using the sup norm in the Cartesian product and the Cartesian product written in the inverse order. Instead of a Cartesian product of x with y, the Cartesian product of y with x. Then, if we consider the sequence x sub n, y sub n, a collection of points in the graph of T, then this must also converge. And what we've done differently in these two places is up here, we were considering the graph of T inverse. So up here we had points y comma x, points y comma x. Well, when we consider points related to the graph of T itself, we'll have x comma y's and x comma y's. But saying the sequence yx is the limit, the sequence y sub n, x sub n has the limit yx, this sequence converges to that. Since we're using the sup norm, implies that if we reverse the order here, we get a limit which consists of this vector with the components interchanged. Sup norm uses the maximum of the two, so we get exactly the same kind of behavior if we look at the norm of yx minus one of these as we would the norm of xy minus one of these. We're using the maximum, so those are going to behave in exactly the same way. So we can reverse the order on the points, and that gives us a sequence which will converge to the point here with the coordinates reversed. T is closed. It's hypotheses. T is closed. So that means the graph of T is closed. That's the very definition of what it means for T to be closed. Here we have a limit of a sequence of points in the graph of T. The graph of T is a closed set. So that limit point must be in the graph of T. Again, Theorem 2.2.a part 3. It's an equality. It's really an if and only if result that we're using with that. But same idea taken in the other direction. So since we have a closed set, then this limit point must be an element of that set. And if we have the pair xy in the graph of T, that means y equals T of x. That's how you get to be in the graph of T, is to satisfy y equals T of x. But if y equals T of x, that means x equals T inverse of y. Ain't no problem with T inverse. We started with a one-to-one mapping T. So if x equals T inverse of y, that means in terms of the graph of T inverse that the pair y comma x is in the graph of T inverse. So what we've shown is if we take an arbitrary yx in the closure of the graph of T inverse, that point y comma x is also in the graph of T inverse. In other words, the closure of G sub T inverse is a subset of G sub T inverse. Well, it works the other way around. I mean, the closure certainly contains everything in the set by definition. So we can draw the conclusion that the closure of the graph of T inverse equals the graph of T inverse, as we've done in several proofs before, showing that this must be a closed set because this is a closed set. So T inverse, the graph of T inverse, is a closed set, topologically closed set in the Cartesian product. And that means, by definition, that T inverse, the transformation itself, is a closed transformation. That's what it means to be a closed transformation, is that the associated graph is a topologically closed set. So there's the first result. Second result, let's just go ahead and look at it in the Beamer file, follows next in the notes. Quick little lemma, I'm not sure Promislow explicitly states this, but if T is a linear transformation from X to Y, and X and Y are Banach spaces, and T is bounded, then T is closed. So here's some conditions under which boundedness implies closed. The condition of being a linear transformation between Banach spaces. So the completeness must come in there somewhere. It's kind of hidden, but it's in there. All right, we want to show T is closed. All right, then we want to show the graph of T is closed. So take yourself a sequence of elements in the graph of T. Suppose this sequence converges to something. Remember, we're measuring, or we're using the soup norm to measure distances in the Cartesian product. So this X sub n, Y sub n converges under the soup norm to something, call it XY, that's the setup. Since we're using a soup norm, then that implies that the sequence of X sub n's converges to X, the sequence of Y sub n converges to Y, because we're using the soup norm. So that's awfully useful norm, it seems. We made a comment at some point in the past where we said something like convergence with respect to the soup norm implies uniform convergence. And that's kind of what we're using here. We're using the uniform convergence that the soup norm gives us on the pairs to draw a conclusion of convergence of the constituents of those pairs. So it's kind of analogous to uniform convergence. It's a little out of the way distance to go. Since we only have pairs, remember you're choosing the maximum when you do the soup norm. So whatever corresponding distances we're talking about here are less than or equal to that soup norm. But it follows from, and is similar to the idea of soup norm convergence implies uniform convergence, pointwise convergence as well. Since T is bounded, you have that hypothesis that T is bounded right there, then it's continuous. Theorem 2.6 tells you a bounded transformation is a continuous transformation. That's where the Banach space stuff comes in. So by appealing to Theorem 2.6, that's where we're appealing to the Banach space part of the hypotheses. So consider T of X. That's T of the limit of the X sub n's. The limit of the X sub n's is T. We can bring that limit outside that transformation because we're dealing with a continuous transformation by Theorem 2.6. T of X sub n, well, T of X sub n is Y sub n. That's what the transformation deals with from the fact that X sub n, Y sub n is an element of the graph. That means Y sub n equals T of X sub n. That's how these points got to be on the graph of T. So we can substitute for X sub n, Y sub n, and now we're considering a limit of Y sub n's, but you know the Y sub n's converge to Y. So we can replace that with Y, and what we've shown is Y equals T of X. Well, if Y equals T of X, then the ordered pair X comma Y is an element of the graph of transformation T. So we've shown if we take a sequence of elements of G of T which converges to something, XY, that something has to be in the graph of T. In other words, by Theorem 2.2.8 part 3, again, G of T is closed. Actually, we've shown G of T closure is a subset of G of T. We've drawn the conclusion as in the previous argument that g of t equals g of t closure, and that's where the closure is coming from. Well, if the graph of t is closed, then t itself is a closed transformation, because that's what it means for a transformation to be closed, and there's the conclusion as claimed. Back to the notes. With a quick little example, not necessarily involving Banach spaces here, so it's a little bit of a special case. But suppose x is the continuous functions on the interval 0, 1 under the sup norm, and y is the elements of the continuous functions on 0, 1 such that f of 0 equals 0 under the sup norm. All right, so continuous functions in x, and y is, I'm sure it's a subspace of x, but we're just treating it as another normed linear space under the sup norm. Y is those continuous functions which take on the value 0 at 0. We're going to define a transformation from the continuous functions into these functions which pass through the origin, I want to say, for which f of 0 is 0, as transformation applied to f produces a function, so we'll let t be the dummy variable for that function, and we're going to define it to be an integral from 0 to t of f of s ds. So we're, in a sense, we're picking an antiderivative. I guess I might have some concerns. Can you do that? Can you always trust this integral to exist if we're taking, say, Riemann integrals? Sure. The function's continuous. Remember, the C in this space means continuous. Yeah, Riemann integrals exist for continuous functions. So I got no problems with the existence of the integral. And what this will produce, by the fundamental theorem of calculus, this will produce an antiderivative of f. What kind of antiderivative? Because there's potentially bunches of antiderivatives. Well, notice what will happen. If you plug in t equals 0, then this antiderivative on the right-hand side of this equation at 0 will be 0. Integral from 0 to 0, blah, blah, blah. Integral from 0 to 0 is 0. So you're taking this function f from space x, as given here, and you're producing a function. It's also going to be continuous by some theory of calculus 1 until it's differentiable, so it's continuous. And when you plug 0 into this new function that you're producing, you get 0 out. When you plug 0 into the new function, you get 0 out. In other words, that new function lives in 0. More pragmatically, what the transformation does, it anti-differentiates f and then gives it a constant of integration to ensure that when you plug 0 in, you get 0 out. I can't say just pick an antiderivative, because that's not well defined. A given function has potentially lots of antiderivatives. If it's a continuous function, I can say pick an antiderivative and make sure when we plug 0 into that antiderivative, we get 0 out. That's what transformation t is doing. T is 1-to-1. A given function under these conditions can only have one such antiderivative. So t has an inverse. And in fact, that inverse is differentiation. So we're looking at an inverse transformation here. We were just talking about, from Theorem 3.7, about the inverse transformation being closed. So we can draw a conclusion from that. Maybe a little bit additional observations here. It's hard to find an inverse of differentiation because of the arbitrary constant stuff. This is one way to work around it. So what we've got here is an inverse of differentiation. Transformation t is an inverse of differentiation. Yeah, it's anti-differentiation with some bells and whistles thrown in to ensure that it's well defined. T is bounded. The transformation given here is bounded. I'm going to leave it to exercise 2.16 to establish that. So if we have bounded transformations on Banach spaces. This is a Banach space. So I'm a little less clear on the fact that this is a Banach space. The soup norm helps with such things, but it's a closed subspace, so it must be itself a Banach space. A bit of details missing on this claim that these are actually Banach spaces. So T is bounded, defined on Banach spaces. The lemma tells us that T is closed. So we have a closed, going back to theorem 3.7, a closed transformation, which is 1-to-1. That implies T inverse is closed. And that's the conclusion here, that T inverse is closed. Next, the last result in this section is called the closed graph theorem, and relates, in the Banach space setting, relates closedness of a transformation to boundedness. Oh, and remember, if a linear transformation is bounded, then it's continuous between Banach spaces. Theorem 2.16. I'm not going to remember the numbers, but we've used that one enough. I remember the number even. So closed graph theorem formally says if T is a linear transformation from X to Y, where X and Y are Banach spaces, then T is closed if and only if it's bounded. The proof, I'm going to bounce back and we'll look up the statements of a few of the things we're going to use in the proof. So I'll keep that stuff in the background. First, lemma 3.5.a, the previous result we proved, shows that if T is bounded, then T is closed. So it's the other direction we need to worry about. So suppose T is closed, we need to show that T is bounded. What does closed mean to you? It means the graph G sub T is topologically closed. So that's what we get from this. We'll consider P sub X to be the projection that maps the graph of T onto X, defined by simply taking the ordered pair and mapping it to X. Take the ordered pair X comma Y and pull off the first component. Similarly, define a projection onto Y that maps the graph of T onto Y. Let that be defined by P sub Y of X comma Y as simply the Y component of that pair. Since we've equipped the Cartesian product with a soup norm, if an ordered pair XY has soup norm 1, then either X has norm 1 or Y has norm 1. The bigger of the two is 1, soup, maximum, when we only have 2 to deal with here. So if we look at the norm of P sub X of X comma Y, well, P sub X of X comma Y is simply vector X itself. Vector X must have norm less than or equal to 1 if vector X comma Y has a norm of 1, since we use a soup norm. So we get the norm of P sub X of X comma Y, where X is a unit vector, to be less than or equal to 1. What we're going to show is we can make that equal to 1. What we get from this is that the operator norm of P sub X is less than or equal to 1, is what we have now. Let's show we can attain that maximum of 1, that supremum of 1. Consider the vector X comma 0. Hey, if X comma 0 is a unit vector, that is, if X is a unit vector in Banach space capital X, then if we'll apply the transformation to that vector, then there's an example where we get equals 1 out. So when we look at the operator norm, remember that was defined as a supremum of all such these as we allow the input, xy, to range over unit vectors. Well, here's a specific unit vector at which that maximum of 1 is attained. So that maximum, that supremum, in the definition of the operator norm of P sub X must be 1. Similar story for Y, exactly same argument for P sub Y. So P sub X and P sub Y are both bounded. X and Y are Banach spaces. Hypotheses, Then the Cartesian product of x and y is a Banach space. Cartesian product of Banach spaces is Banach spaces. Theorem 2.10.a, like I said. In the likely event you don't remember all of this stuff, let's jump back and look at some of these things. Theorem 2.10.a said, if x sub s is a Banach space, and we look at the Cartesian product of x sub s's over any indexing set S, then the Cartesian product, the direct product, is a Banach space. So direct products, Cartesian products of Banach spaces are Banach spaces. Theorem 2.10.a, back to the proof. So x times y is a Banach space. G sub t is closed in x times y because we've assumed t is a closed transformation. That means the graph of t is a topologically closed set in x times y. So G sub t is itself a Banach space. How's that sound? Closed subset of a Banach space is itself a Banach space. Theorem 216. Let's go look that one up. Theorem 216, a subspace Y of a Banach space X is itself a Banach space if and only if Y is closed, if the subspace is closed. Here the subspace is the graph. The graph is closed, the big Banach space is the Cartesian product X times Y. But applying Theorem 2.16 gives us that G sub t is itself a Banach space. The graph of t is a Banach space. The range of the projection is all of x. Think about it. Transformation t is defined on all of x. So when we go looking at, where's a convenient place to point to it? When we go looking at ordered pairs x, y, hey, x, all values of x are present. I don't know if all values of y are present. I don't know if this transformation is onto, is surjective. But no matter how you slice it, all of the x's appear because the domain of x, the domain of transformation t is all of space x. T is defined on space x. I mean, that's what part of the meaning of these symbols is. T maps all of this space into that space. So I don't know about onto, but I do know the domain is this space. That's the meaning of the notation. So t is defined on all of x. P sub x includes, therefore, all of x, projects those pairs onto this space and includes all elements of this space. So the range of P of x equals all of x. Space x is closed in itself. So here we have a mapping with a closed range. Theorem 3.6 told you if the range of a linear transformation is closed, then that linear transformation, then the inverse of that linear transformation is bounded. Let's look at Theorem 3.6. So we're looking at closed range implies bounded inverse. 3.6, we've got closed range. Closed range implies bounded inverse. Of course, we need it injective to talk about the inverse here. We're talking about P sub x this time, right? So the transformation is not t, it's P sub x. So we just showed the range of P sub x is closed. From that, we can conclude that P sub x inverse is bounded. P sub x inverse is bounded. We're trying to show t is bounded. That's what we're working on. T is bounded. Well, we can write t as a composition of P sub y and P sub x inverse. So let me try to convince you of that. P sub x inverse would map us from x into the graph. The projection mapped, here it is, the projection mapped the graph into x, actually mapped the graph onto x. So P sub x inverse takes x and maps it to the graph. P sub y projects the graph onto y. So what we get in this composition is a way of expressing t, which maps x to y, as mapping x through the graph and then to y. Compositions are usually interpreted like that. So we can actually write t as this composition, p sub y, composed with p sub x inverse. Remember, when transformations are written side by side like that, it means composition of the transformations. I wouldn't mind putting a little circle in between them to be more explicit, but that's the meaning of what we have here. And when we were looking at the norm of a composition, it was proposition 2.8 that told us the norm of the composition is less than or equal to the product of the norms of the constituent transformations. Let's look finally at proposition 2.8 from section 2.4. When we had a composition, ST, the norm of the composition is less than or equal to the product of the norms, the operator norms. And that's what we need here. P sub y is bounded. We said that up here. P sub y is bounded. In fact, its norm is 1. And P sub x inverse is bounded. We went through an argument about that given here. So this is bounded and this is bounded. So the norm of t equals the norm of this composition is less than or equal to the norm of P sub y times the norm of P sub x inverse. Norm of P sub y is 1, conveniently, and P sub y inverse, its norm is finite because it's bounded. So the norm of t is bounded as well. That is, t is a bounded transformation. T closed implies t bounded in this setting, and that's the closed graph theorem. And that's the last thing in this section. We have one section left in chapter 3. We'll introduce a new kind of boundedness called uniform boundedness in the next section. It's not a very long section either. We'll finish that up, and that'll take care of chapter 3, and then we'll move on into Banach spaces in chapter 4 is at Hilbert space, and maybe we're the Hilbert space stuff by now. But making good progress. I'll see you in the next section shortly. Have a nice day.